Hello everyone, this is Miss Salter. This is the part 2 video of the heat of vaporization and heat of fusion video summary. Didn't have enough time in the last video to finish up number 5 of the examples, and it is a rather large one, so I wanted to make sure we had plenty of time to just kind of go over it and make everything as clear as possible. So we're going to start out here with, this is the color-coded kind of section for a phase change diagram for water. It's for water only because of the temperatures that are on the left-hand side. It's the same type of thing for many substances. You have this line that has slopes where we have a temperature change. The phase of the material stays the same during that slope as the material heats or cools, and then when it gets to a plateau, a flat spot, that's when we have our phase change. The temperature of the material stays constant, but the phase of that starts to shift. So in the orange part there, you'll see we are either having a melting or a freezing. That's a heat of fusion. In the pink part, we are having either a boiling action or a condensing action. That is a heat of vaporization. If it is, the arrow is going to the right, it means it is endothermic and taking in energy in order to do the phase change. If the arrow is going to the left, that means it is giving up energy to do the phase change. So, I have also on this diagram here where what equation you are using for each section, and that's going to be very important. You have to keep that in the back of your mind. And the change in temperature for these guys, when we do change in temperature for this equation, say here in the light blue part that I'm kind of focusing on with my cursor, we're only doing a change of temperature within the blue part. Once we get to a plateau, we need to stop and calculate a phase change. So if you have a material that starts in the light blue and travels and heats up and then goes through a phase change and then heats up some more and ends up with a temperature up here in the green part, you need to split that into 3 hunks. One part for the change in temperature in the blue. Then you calculate the amount of energy needed for the phase change. Then you calculate the energy for the change in temperature as a gas. So it depends on what temperature you are initially, mainly starting with and finally going to, but you may have multiple steps. Don't forget with water, ice is a solid. The liquid we kind of call just water or liquid water, and the gas is a steam. Okay, so next thing we are going to do is scroll up here to the top of example number 5, and we'll start in this part here at the top. Just said something about I think water constants. These are the different water constants that I have that we are talking about in these different problems. I just listed them all here in case I needed them, so they're all in one place. So number 5 says, how many joules of energy are required to heat 200 grams of water from 25 degrees Celsius to 125 degrees Celsius? Water boils at 100 degrees. So that last part is just kind of a hint. It's nice that was included in the problem, because that tells us that we have a phase change in the middle of our change of temperature. So, step 1, when you've got something that seems a little more complicated, even with the regular problems, I didn't do it in 1 through 4, look at the phase change diagram. Use your finger, figure out where the temperatures are, make sure that you are doing work either within just the phase change or just as a temperature change. You are not switching at these little break points in the diagram because that means you're going to have to do one like number 5. So step 1 here, we're going to draw a phase change diagram and label the temperatures given in the problem. So I just did an easy drawing here. I've got my slopes for my 3 phases. I've got my 2 plateaus for my phase changes. I plotted in my 0 and my 100. I went from 25 all the way up to 125. Oh no. Because I'm going from 25 to 125, I have a phase change in the middle. The temperature stays steady at 100 degrees during that phase change, but I've got a multi-part problem here. I've got 2 temperature changes, one that goes from 25 to 100 as the liquid. Then I go through a phase change. Then I go from 100 to 125 as a gas, as steam. So, step number 2, let's make a plan. Very, very important. We're going to use this idea that we had from reaction conversions. We're starting with water as a liquid, going to water as a liquid, but we're changing our temperature from 25 to 100. That means we're going to use, this is part 1, we're going to use Q1. We're going to qualify this as a Q1 because we're going to have multiple energies here that we are calculating. This is going to be MC, change in temperature for the liquid. We are counting only the temperature up to the phase change, only the temperature as a liquid. So we're going from 25 to 100. In part 2, this is a phase change. We have to change this because we're using a different equation. Here, when I write this out, I'm going from water as a liquid, transferring to water as a gas, but my temperature stays the same. Both sides of my arrow here on my plan have 100 degrees. So therefore, I am using Q2, subscript 2, equals M times the heat of vaporization. Vaporization, because we are vaporizing our liquid and making a gas. Then I gotta go, and I'm going from gaseous water to gaseous water, but I've got a temperature change from 100 to 125. My temperature change is going to be part 3. Q3 equals MC, change in T, as a gas. This is the change in temperature only in the gas phase. So I've split my initial full 100 degrees into 2 chunks because that's how I have to handle them since my C values are different for each phase. So my C value for my liquid phase is going to be 4.184. My C value for my gas phase is 2.02. Since those two are different, I need to split this problem up. So I've got a part 1, a part 2, and a part 3. Now, part 1 and part 3 we have seen before, okay? Part 1 and part 3 are going to be just like, hold on, just like, well, it's like kind of like number 4, but backward. Ugh. And number 3 is just like part 3. So, let's get on to it here. Okay, step 3, we solve each part. Don't forget, every phase has a different value for its specific heat capacity. That's what makes part 1 and part 3 different. We have to treat them differently. I color-coded these. If you see, the diagram color is the same as the plan color, is the same as the part color. I'm trying to make this as clear as possible for you guys. So here, part 1, we have a temperature change as a liquid. We're using Q1 equals MC, change in temperature as a liquid. So 200 grams times 4.184 times, and this is only the change in the temperature as a liquid. So our final temperature as a liquid is 100 degrees. Because after 100 degrees, we need to do a phase change. Well, actually, at 100 degrees, we have to do a phase change. So we have to 100 degrees is our final temperature as a liquid. Our initial temperature as a liquid was 25. So that's why we get this 75 value. Do the math, 62,760 joules for the value of Q1. Box it, stick it to the side. Let's keep going. Part 2. Part 2 is a phase change. We're doing liquid to a gas. We're using a heat of vaporization. Q2 equals M times heat of vaporization, 200 grams in this sample. We have a big, huge number. It takes a lot of energy to move water from a liquid to a gas. 452,000 joules. Part 3, the green part, like I said, you can go up here to the plan and to the diagram and see where these pieces are and how they relate. Part 3 is our temperature change as a gas. So Q3 equals MC, change in temperature for a gas. Our C value is 2.02 joules per grams degrees Celsius. This change in temperature is only the change in the temperature as a gas. Our final temperature we're going to is 125. Our initial temperature as a gas is 100 degrees Celsius. That's the breaking point for our phase change. So as a gas, this steam only raised from 100 to 125. So therefore we get 10,100 joules. So step 4, we're looking for the total amount of energy that was used to do this process. So we just add up all the parts to find our total energy. Our total energy is Q1 plus Q2 plus Q3. We add them all together. We get Q of total of 524,860 joules. Most of the time, joules are in even numbers, just because of what we're using. Sometimes some of these questions are figured out that way. And also usually too because we're using such big numbers with such kind of lack of accuracy. The significant figures are off, that usually the joules are rounded to the nearest ones value. There's one on the practice worksheet 3 that I gave you to 2 decimal places. You know, that's the exception. All the other ones that are looking for joules on worksheet 3 are all to the ones place. No big deal. I'm not going to make a big deal about it unless I specify how many decimal places I want. So, final answer on this one is a pretty big number simply because it takes a lot of energy for that phase change. Okay, that is about it. I hope this was helpful, and have a good day.